Haskell comes with a number of predefined type classes and instances. Some of the most used include the EQ type class, which you can use to define equality and inequality. So imagine you have two ints, a number 2 and a number 4, and you want to test if they are equal or not equal. Since int defines an instance for EQ, you are able to use the equals function and the not equal function. And because these are arithmetic operations, Haskell does some magic with these particular functions so that you can place them in the middle between the operands as you would expect. The show type class defines the show function that allows you to convert a value of a type to a string representation. In one of the previous slides, we created our own version, which we called myShow. I just did that as an illustration of type classes. In actual fact, we can just go ahead and use the inbuilt show type class and the show function to achieve the same thing. The inbuilt Haskell show type class includes some additional functions, show prec and show list. The prec stands for precedence. It's not important to understand these two additional functions since Haskell provides default implementations for them. We will cover default implementations in type classes later in this module. The bounded type class is used to define the upper and lower limits of a type. So, for example, we know with the int type that it has a min bound and a max bound, and we can see what it is because int defines an instance of the bounded type class. An int cannot store a value lower than the min bound or a value higher than the max bound. There is also a type class called ord for ordered types. Before we look at the function signatures, there is something different about this class declaration. This type class definition has a type class constraint in it. What this means is that any type which wants to define an instance of ord must also have an instance of the EQ type class defined for it. So, in addition to the functions compare, less than or equal to, etc., the type also needs to have defined implementations for equals and not equals. This is how we can build up type class hierarchies. An int defines an instance for ord, and we can see the usage of the functions in the type class here. When we compare 1 with 5, we get a value of LT back, which is an ordering. LT here means less than, because 1 is less than 5. When we test if 1 is less than 5, it is obviously true, and we get the expected results for the rest of the function calls as well. Now I'm not going to show the definitions for all of the inbuilt type classes, but there are some key additional ones which you should know about. The read type class is essentially the opposite of show, whereas show takes a value and returns its string representation, read takes a string and returns its value representation. The enum type class defines operations on sequentially ordered types. So since an int defines an instance for this type class, I can ask for the successor of a value. So I could ask for the successor of 4 and get 5, and the successor of 5 and get 6, etc. There are also a number of different type classes which are defined to represent the different operations for different numeric types. All of these type classes form a hierarchy which is visible in the image on the right. For each type class in the prelude, you can see which types in the prelude define an instance. So for example, for the EQ type class, all of the types defined in the prelude have an instance for it, except for the IO type and this weird type with the arrow. Just ignore that weird type for now. For the num type class, the int, integer, float and double types define an instance. We can also see the hierarchy quite clearly by following the arrows. So, for example, the ord type class has the constraint that the type must also have an instance of the EQ type class. And so if we go to the deepest type class in this hierarchy, the real float, we can see that any type that defines an instance of a real float must also have defined an instance of real frac and real and ord and num and EQ and show and floating and fractional. So if you have a type which defines an instance of a real float, which in this case would be a float or double, then you can do all of the operations defined in that type class hierarchy. This video is a clip from a longer video for beginners starting with Haskell. Check that out if you would like to see all of the content. Also check out the entire Introduction to Functional Programming with Haskell course on the Learn channel. See you next time.